All right, a mistake was pointed out right after we shut off the camera here. Obviously, I made a mistake here. The inverse of 9 is not 1, it's itself. 9 times 9 is 1 this term. All right, now we're on to the dihedral groups. Dn represents the group of all symmetries of a regular n-gon. A regular 3-gon is an equilateral triangle. A regular 4-gon is a square. Regular 5-gon is a pentagon with equal side lengths and equal angles. Regular means equal side lengths and equal angles. Regular 6-gon is a hexagon with equal side lengths and equal angles. It's called the dihedral group of order 2n, meaning it's got 2n elements in it. The elements are functions. They're transformations of the plane that leave the object looking the same. They are rotations and reflections, as you've read about. Let's go to our low technology here and think about this. I was going to do it with high tech. I was trying to get Mathematica to do it for me, as you might have guessed. But I was being unsuccessful. I'll show you what I did real quick after we do the low tech approach. Overhead projector, yay! Let's see. And thankfully, I was looking for a protractor this morning, but I couldn't find one. Thank you. You have one here. To try to make these angles as good as possible, it's good to try to make this drawing as good as possible. I'm going to draw an equilateral triangle. Not just a straight edge, but a ruler so I can make the lengths right. You can't see those lengths, but let me make the side lengths. I'm going to make them 2 inches on the thing here, though it's going to be bigger than 2 inches up on the screen. So that's about 2 inches on the transparency. Now I want to, now I'm making it horizontal, that's okay. Measure the angle to be 60 degrees here. Right about there. Measure a side of length 2. Right about like that. And then the other side should be length 2 as well. And is it coming out well? Yeah, it's coming out pretty good. This is a pretty good drawing here. It's pretty close to a perfect equilateral triangle there. D3 would be the symmetries of this equilateral triangle. It's helpful to color the vertices different colors. So that one's blue. This one's red. And this one over here is going to be green. As you've read about, the elements over here consist of rotations. R0 is no rotation, no motion at all. R120 is a rotation counterclockwise, is the convention we will use, by 120 degrees. 2 pi over 3 radians. R240 is a rotation counterclockwise by 240 degrees. So I'll bring you down here. V is a reflection across a vertical line here that's going to be perpendicular to the base, going through the vertex at the top there. It's going to be a flip, watch, this way. Actually, I should really make 2 drawings, shouldn't I? To see this more perfectly. But, so I can have one in the background and this one that goes on top of it. But I won't take the time to do that. D is a trickier reflection across a diagonal that's going to go, like my hand here, perpendicular to this side, going through that vertex. I'm labeling it D because it's kind of like a main diagonal. D prime is the other one, the off-diagonal one, a reflection across this line, perpendicular to this line segment and going through that vertex. Can I fill in the Cayley table? Well, I hope it's pretty intuitive that when you compose the rotations with each other, you just get another rotation. R120 composed with itself is rotate by 120 degrees, then another 120 degrees. That's going to be R240. If I compose R120 with R240, I'm going to get back to where I started. 120 degrees, then another 240 degrees brings you back to where you started. And if you do two 240 degree rotations, it's the same geometric effect in the end as doing just one 120 degree rotation. 240 degrees brings you to here. Then if you do another 240 degrees, it brings you back over here. Same end effect as just doing a single 120 degree rotation. So we can think of it that way. The imagining as far as these rotations go is just that. It's just imagining. What's really most important is the end effect of these functions. These are, this composed with this is the same as that function as far as where the points end up, the images. Oh, I don't know that I'm going to have time to do all these here. Let's do a few of them at least. I'm saying I don't have time. Let's compose R120 with D, for example, or with V. R120 with V, and remember this is function composition, so the operations go from right to left as far as which gets applied first. So I'm going to do V first and then R120. Remember the original orientation of the colors here, blue on top, red on the left, green on the right. Try to remember that. So here we go, V reflects it this way across the vertical line, and then R120 rotates it 120 degrees to bring us to here. What's the net effect of that? The net effect is that red and blue got swapped, right? Blue used to be there and red used to be there. Green stayed there. That's the same as D, a reflection across the main diagonal. This is the same as D. If you do it the other direction, do you get the same thing? Is this a commutative abelian group or not? Go back to where we had it here. Blue on top, red on the left, green on the right. Do R120 first. Then do V. What's the net effect? The net effect was to swap the blue and the green that time. The blue was up here, the green was down there. That's equivalent to D prime. In the Cayley table, the convention we will do is that when we do R120V, R120 on the left, V on the right, start with the column there, R120, and then end with the, start with this column, then end with this row. So R120V, that composition has an answer that goes in that spot. That's D. Do it the other way around. V R120, go to V here and R120 there. They meet right there. D prime should go there. Right away you see the matrix is not symmetric now. Across the diagonal here, D prime and D are not the same. This is a non-abelian group. Let's compose two reflections, and I'll stop it there. We'll do it both ways, though. Let's compose V with D and see what we get, and D with V and see what we get. Go back to the original orientation, blue on top. V with D means do D first. Watch carefully. D first, reflect across this line. Like that, swap the red and the blue. Then do V across this line, the vertical. Swaps the green and the blue. What's the net effect? Should be a rotation. The blue was originally up there. It's been rotated by 240 degrees to there. Same with the red and the green. They've been rotated by 240 degrees in the counterclockwise direction. This is R240. Now do it the other way, dV, meaning do V first. There's the original. V gets done first, so I reflect this way. Then D gets done, so I reflect this way. I'm left with a rotation. It's a 120 degree rotation from the original. The blue is on top of the original. It's been rotated by 120 degrees, and same with the other ones. So dV, right? Okay. VD right here is going to be R240. And dV right here is going to be R120. Once again, emphasizing the fact that this group is not abelian. Okay, and I could continue. I won't take the time. Maybe I should get this back to you before I forget. I was thinking about doing the symmetries of square too, but the book does that. And we only have a limited amount of time. So I better not, as much fun as that was. I did try to get Mathematica to do this, but believe it or not, I was having trouble getting it to be ideal. I did make a Cayley table in Mathematica, but it was not with doing anything fancy. Stored the text in these variables and then just made a big table with table form and table headings, and there we go. Nothing fancy there, just doing it brute force. I'll put that in the same folder on Google Drive. You can look at it if you like. As far as doing the visual transformations themselves, I tried using like rotation matrices. Here, doing the rotations is not much of a problem. Oh, I colored it differently. Oh well. However, doing the reflections is troublesome because you need a third dimension. And I was able to rotate in that third dimension, and you can rotate this to see the triangles in that one plane. But I was having trouble trying to figure out how to also have a slider for a flip that would do things appropriately. Here was my last attempt. Actually, let's see. And these just do the individual rotations here, R120 and R240. And I can combine them as well. I tried doing one reflection, and it almost worked, except when you do the reflection like that, then you do the other rotation, it goes the wrong direction. So it was not working. So these are my attempts so far, is to program this in the Mathematica, but I'm unsuccessful so far. Okay, not sure if I'll keep working on it or not. Depends on how much time I have. Here's an example of how you think about reflections in D6, symmetries of a regular hexagon. The lines of symmetry for the reflection would be these 6 lines. It looks like more than 6 lines, doesn't it? But it is 6. 1, 2, 3, 4, 5, 6. Some of them go through the vertices, half of them go through the vertices, half go through the midpoints of the sides, of the edges. Those are the lines of reflection for symmetries in D6. This is a review about equivalence relations. Are just emphasizing, first of all, that our most important equivalence relation so far is congruence modulo n. Why not just call it equivalence modulo n? Well, it's historical. They used to just call it congruence. A is congruent to B mod n if and only if there is an integer k, so that this is true. N divides A minus B, in other words. N would also divide B minus A. The symmetric property holds. Important things about this, like always, equivalence relations partition. So this partitions the integers in such a way that the collection of equivalence classes, like I talked about last time, can be defined to be a group that is isomorphic to Zn. Has the same form. We aren't going to precisely define the idea of an isomorphism for a while. I think it's maybe chapter 7 or 8. Essentially, you can think of, for example, Z4 as being either this collection of 4 symbols, 0, 1, 2, and 3, under addition mod 4, excuse me. Or you can think of Z4 as being a collection, not really of numbers, but of equivalence classes of numbers. Under really addition mod 4, you could still call it that. You could still call it addition mod 4. Where, again, essentially, you add 2 equivalence classes by adding their representatives and then doing mod 4. Write that kind of equation. By the way, congruence also applies to geometry. Another example of an equivalence relation that's real important in geometry is congruence. I called it congruence of triangles. I could have just said congruence in general. I did make a successful Mathematica animation here. Two triangles are congruent if you can obtain one from the other by a sequence of rigid rotations or rigid translations where you don't change the distances. That's why I said rigid. So I can translate this triangle, then I can rotate it, and I get another triangle that is congruent to the original. Translate this back, rotate again, get another triangle congruent to the original. That's an equivalence relation. A triangle is congruent to itself. You do not have to do any actual translations or rotations. You can call that the identity transformation. If a triangle is congruent to another, via a series of rotations and translations, you can go backwards to say that the second one is congruent to the first. And if one triangle is congruent to another, and that triangle is congruent to another, you can say the first and third are congruent because you can do the transformations of the plane in sequence, like I just showed you. Okay? Just worth mentioning, I think. The idea of an equivalence relation has broad application. All right, only 5 more minutes. I think what might be most important to emphasize in our final 5 minutes is the usefulness of the GCD as a linear combination theorem. Now, we did use it last time. Not from the beginning. We did use this last time in a proof. And I wanted to have time for a full proof of the following thing today, but we only have a few minutes. So maybe I can only give you the idea of the proof. It's of a homework problem that was actually not assigned, but I referred to it. Exercise 5, page 24 if you want to look there. It's to show that you got 2 positive integers, a and b, say. A times b can be also calculated by doing the GCD of a comma b times the LCM, least common multiple of a and b. If you look in the back of the book, they prove that using prime factorization, which is fine. But you also can use the GCD as a linear combination theorem. Although, what I talk about here at first, I will not use that. Let's call the GCD D for divisor and call the LCM M for multiple. First step in trying to see why this is true is to maybe realize it's equivalent to AB equals DM so that M equals AB divided by D. If I could prove that's true, then I'd be done. And part of proving it's true, where M is the least common multiple of A and B, would be showing just that this thing is a multiple of A and B. That would be part of the proof, right? To be the least common multiple, you first want to show it's a multiple. And then maybe you want to show it's the least possible multiple. Showing it's a multiple does not require the GCDs of the linear combination theorem. It just requires using the fact that what these things are. D being the greatest common divisor means D is a divisor of A and B. So for example, A would equal, say, A prime times D. Well, let me use a subscript. Let's say A1 times D for some number A. By the way, these are integers here. So multiplication would be commutative. And B would say be some other integer B1 times D. Look at this fraction again, AB over D, that I'd like to ultimately show is the least common multiple of A and B. Is it even a multiple of A and B? Well, for example, if you replace A by A1 times D, these are integers here. This is a rational number. We know you can cancel the D's. And you get A1 times B. In other words, AB over D is a multiple of B. And a similar kind of calculation would show AB over D is a multiple of A. Replace B with B1 times D. And once again, cancel the D's. So AB over D is a multiple of A. So that's a multiple. But does it equal M? Does it equal the least common multiple? Notice I've not written an M yet here because I'm saying M is the least common multiple. How would you show it's the least? You could show it's the least by showing that any other multiple of A and B has the property that M divides that multiple. Any other positive multiple of A and B has the property that M divides it. Then M would have to be the least one. So we're talking positive integers here. Suppose, say, I don't know, N is a multiple of both A and B. Maybe A2 times A and B2 times B. We would be done if we can show M divides N. Where I should really not call it M yet. We can be done if we can show it AB over D divides N. It is an integer, AB over D, because it's a multiple of A and B. It's a fraction that can be reduced, though you can't reduce it as you see it here. And again, we're assuming we know how to deal with rational numbers here. I could look at this rational number and I could rewrite it like this. I guess I am essentially doing the proof here without writing sentences. Here's where you can use the GCD as a linear combination theorem. D is the GCD of A and B. Therefore, there's some S and T where D equals AS plus BT. GCD is a linear combination theorem. Try to simplify it. Does it simplify? You can separate it into the sum of two fractions. What am I hoping about this? I'm hoping it's really an integer. That's what I'm hoping. Is it? Well, the A's cancel here and the B's cancel there. Are those things integers? Yeah, because n is a multiple of A and B. I can replace n with these two things appropriately. In this one, the first fraction, I can replace n with, say, B2b. And the second one, I could replace it with a2a. And then cancel appropriately to get b2s plus a2t, which is an integer. So I guess I had the time. We're out of time right now. Oh, a couple minutes over, sorry. To go through the proof without writing sentences. That's the idea. That's, again, to emphasize the usefulness of the GCDs that we kind of go through. See you on Friday.